Good morning, Mr. Chairman, ladies and gentlemen. I'm so proud and honored to have the opportunity to speak at this webinar. My name is Yanshan Huang. I'm from Shanghai Institute of Technology. I received my PhD degrees in the group of Professor Xin Feng in Shanghai Jiao Tong University in 2015. My interested research focused on graphene-based flexible electrodes for energy storage. Today, I'd like to present some of my work's graphene-constructed flexible electrodes for lithium-ion batteries. My presentation will cover the following aspects. First, let's look back at the development of rechargeable batteries history. In the past, the rechargeable batteries were huge and large, so they could only meet the industry demand. With the development of science and technology, the rechargeable batteries can be designed in many shapes and applied in many applications. The application of the rechargeable batteries has transferred from industry demand to personal demand. Now we can find the batteries everywhere and every time in our daily life, such as in laptops, in smartphones, and in vehicles, and so on. In the future, the flexible and wearable device has become more and more popular in high-tech fields. So, the research of the flexible and high-capacity rechargeable batteries has become one of the most important in the future. Graphene has received considerable attention in the energy storage field because of its unit 2D structures, high conductivity, and excellent mechanical properties. So today, the graphene has become one of the most important base materials to fabricate the electrodes. Today, I'd like to introduce some of our works about graphene-based flexible electrodes. First, we used the metal organic framework MOF as the metal oxide precursor and design assembly of porous ferric oxide into 3D phosphorus-poped graphene frameworks by in-situ growth and thermal process. The detail are as follows. The ferric oxide, ferric ions, and cyanide reagents were reacted to form Prussian blue, a typical MOFs, and this Prussian blue PB can be tightly attached on the graphene by electrostatic interactions, and the PB graphene can be constructed to 3D structures by cell assembly method using sodium ascorbate as a reducing agent, and after annealing at air in the air at 300 degrees the Pb can be transferred to porous ferric oxide, and the outer annealing in nitrogen atom sphere at 350 degrees, and using sodium dihydrogen phosphate as source, the phosphorus-poped can be successfully doped in the graphene. From the TM, we can find the porous ferric oxide can be uniformly disposed on the graphene surface. The morphology of the compost can be characterized by SEM and TM image. From SEM, we can find the compost was with 3D structures, and both SEM and TM image showed that the ferric oxide particles were homogeneously dispersed on the graphene surface. From the high resolution of TM showed that the crystal latitude of the particles is 0.25 nanometers. This was corresponded to 110 planes of alpha ferric oxide. From the mapping, SEM mapping showed that the carbon, oxygen, iron, and phosphorus were homogeneously dispersed on the compost. Benefit from the robust 3D interlocked graphene sheets, the compost monoliths can be directly compressed into a flat film electrode, and the film can be bent nearly 100 times without deformation or crash. From the side view of the SEM, we can find after compressing, the film was with compact layer structures. The flexible electrodes manifest excellent performance when used band-free electrodes for lithium-ion batteries. Even at bending state, the compost can deliver a capacity of 466 mAh per gram at current density of 3000 mAh per gram after 6000 charge-discharge cycles. We also use cobalt oxide prepared cobalt oxide graphene composed with nitrogen-doped carbon layers. Here we use cobalt reagents as the MOF as the cobalt oxide precursor, and polyaniline penny as the nitrogen-doped carbon layers precursor, and the graphene as a self-supporting frameworks. And the compost also can be directly compressed as a flex films. Without penny layers protect the cobalt oxide, the cobalt MOF can be transferred into the cyanide regions in the MOF or decomposed outer annealing, and the MOF can be transferred to cobalt oxides and pulverized into small pieces. With the penny layers, coating layers, the after annealing, the cobalt MOF or directly transferred to carbon dioxide cluster crashes. The reason is that panic layer was converted to nitrogen-doped carbon layer and coated outside the MOF, and the cyanide reagents decomposed to nitrogen-containing gas and directly carbonized as carbon channels in the crashes. So the mapping showed that the carbon, nitrogen, oxygen, cobalt elements were homogeneously dispersed in the compost. With 3D structures, excellent mechanical stability, and nitrogen-doped carbon layers, the compost showed excellent performance when used as flexible anode for lithium-ion batteries. The compost delivered 1,490 mAh per gram at a current density of 100 mA, and the capacity can still remain 1,100 mAh per gram after 110 cycles. Without nitrogen-doped carbon layers, the carbon dioxide graphene frameworks only delivered 750 mAh per gram at the same condition, and the pure carbon dioxide only showed 100 mAh per gram. And the compost also showed excellent rate performance. Even at 8 amp per gram, the capacity can deliver 337 mAh per gram, and the current density returned to 100 mA per gram. The capacity can recover to 1,200 mAh per gram. The compost also showed promised super long cycling performance. The capacity can deliver nearly 400 mAh per gram after 1,200 cycles at a current density of 1 amp per gram. The mechanism is that the nitrogen-doped carbon layers and the channels can promote the ion diffusion and electron transport, and also these carbon layers can protect the metal oxide and help releasing the volume expansion effect of metal oxide during charge and discharge process. And the 3D graphene frameworks can shorten the diffusion of the ions. So finally, I'd like to make a conclusion of this presentation. 3 main points can be summarized. The graphene framework has become one of the most important best materials to fabricate flexible electrodes, and it can shorten the diffusion distance of the lithium ions. And the MOF-derived metal oxide flexible electrodes can easily adjust the metal oxides with porous structures. These unique structures can facilitate the ion diffusion and electron transport. And we also can introduce some heteroatom atom-doped carbon layers. These carbon layers can not only relieve the value its volume expansion effect of the metal oxide, and can also provide multi-mini-parent channels for electrodes during charge and discharge process. So the percent synthetic method will applied to fabricate other 3D structures for the application of energy storage. At last, thanks for your kind attention, and I'm pleased to make this presentation. I also deeply thanks the funding support and my supervisors and the college and the students. Thank you.